Welcome to lecture number 3, Chemical Kinetics. So we have been discussing the different methods of determining order and rate law of an unknown reaction. So far we have discussed integration method and the differential method. So I told you there were 4 methods we are going to study, so 2 of which we have already covered. So now let's look at the third method, that is the isolation method, also known as Oswald's method. So here we basically take an unknown reaction like this A plus B going to P. So for any unknown reaction, the rate can be expressed in terms of, say, minus dCA dt. So in terms of the disappearance of one of the reactants is equal to rate constant and Ca to the power alpha and Cb to the power beta. So obviously these are the concentrations of the 2 reactants respectively. And here alpha and beta are unknown. We don't know. We are going to figure it out. So the question is, what we do in the isolation method. In isolation method, actually we follow the principles of the pseudo first order reaction. So that means what we do, we actually take, so for example, for a reaction like this, we take the reactant B in a very large excess. So large that this rate equation can be represented as K prime Ca to the power alpha, because we take Cb as the means the initial concentration of B is much higher than the concentration of A. Okay, so this is the consideration. So it means the concentration of B remains virtually constant throughout the reaction. So then what happens that we have this rate equation now. So now we can easily apply either the method 1, that means the integration method, or the method 2, that means the differential method, to figure out alpha. So likewise we can do just the reverse process to figure out beta by taking the large initial concentration of A, so that the concentration of A almost remain constant throughout the reaction. But there is only one thing that we should be cautious about this reaction, that while taking one of the reactants at a very large concentration, 2 things we should remember, that it should not alter the mechanism of the reaction, and number 1, that it should not affect the outcome or the product of the reaction. Okay, so now let's move on to the 4th method. Okay, so let's clean the board and talk about it. So the 4th method is known as the initial rate method. It is quite straightforward. So like before, we have an unknown reaction where the alpha beta basically not known, and we have to determine it. So what we do is we run the reaction twice with 2 different initial concentration of A. For example, let's run the reaction with double the concentration of A. Okay, so initial concentration, and so the rate 1, we will measure the initial rate. So initial rate can be expressed something like this. All right, and then we actually run another reaction where we take whatever the concentration we have started with, just half of it, but we don't change the concentration of B. So B remains same, constant. So we can say this is equation 1 and this is equation 2. So this is rate 1 stands for the initial rate of the first reaction, where the concentration of A is double than the second case. So this rate 2 is the initial rate in the second case. So what we do, that dividing equation 1 by equation 2, then we get that we have a ratio, all right? So rate 1 divided by rate 2, it gives me, so these things cancel out, and we have 2 to the power alpha, and let's take this, call this ratio as P. All right. So therefore, we can easily find out alpha is equal to natural log of P divided by natural log of 2. So here we find out alpha. So in the same manner, we repeat the process without changing the concentration of A. We run the reactions twice. First set with double the concentration of B, and in the second set, everything as it is like this. So we change the concentration of B, like whether we can take it double or half or whatever, and then again by taking the ratio rate 1 by rate 2, we can easily figure out beta like this. And this is one of the most popular method to figure out alpha or beta, especially when the reactions are of second order. All right. So these are the 4 methods, and we have discussed the basic principles, and we should take a look, or we should consider these methods for solving some numerical problems. All right. So now let's move on to the next section. So up to this much, it was all the preliminary. So our preliminary part is over. Now let's move on to a little bit deeper into the subject. We start with a section which is called simultaneous reaction. Okay, so let's start that. So now we come into the context of simultaneous reactions. So simultaneous reactions define that there are reactions where the reactants and the products may undergo more than one changes simultaneously at the same time. Okay, so far the first order, second order reactions that we have seen, these are simple, straightforward reaction. That means reactant is just being converted into the product, and that's it. But here now we would look into a little bit more complex scenarios. So together means there are 3 different types of simultaneous reactions we can think of, but we will only study the first order type. That means where the different parts of the reactions or different steps of the reactions would be first order. So that automatically tells that simultaneous reactions contain reactions having more than one step. So therefore, we make a quick classification of these 3 types of simultaneous reactions. So one of the type is A going to B, okay, but B is going back to give A. You have already seen these kind of reactions, didn't you? This is an example of a reversible reaction, okay? But in terms of kinetics, we call this type of reaction as opposing reaction. Opposing means that the direction of A going to B and B going to A are just opposite to each other. Then we have another type, that is A going to B, but again B, like a chain, forms C. Okay, so A going to B and then going to C. So this kind of reaction is called, in terms of kinetics, consecutive reaction. Okay, and lastly, we have a reaction that we have the reactant A, but A simultaneously producing 2 products, B and C. All right, so that kind of reaction is called parallel reaction. But the only advantage of this thing that our syllabus tells us that all these individual steps, so we can write their rate constants, K1, K2, etc. for each of the steps. So all these individual steps would contain only first order mechanism, which is the part of our syllabus. Okay, so now we are going to study these simultaneous reactions one by one. So let's first start with the opposing reaction. Okay, with A going to B and B is coming back to A. So we will study this opposing reaction in 2 ways. Obviously, as we have seen earlier, we can deduce the integrated rate law in terms of appearance of the product as well as in terms of disappearance of the reactant. So here we go. Let's start with the opposing reaction. So let's first deal the reaction in terms of the appearance of the product, that is dx dt. So therefore, we would follow the usual steps, and we are by now we are familiar with it, that at time t is equal to 0, the initial concentration of A is smaller is A, and the concentration of the product B is 0, and at any time t we have A minus X, and the concentration of B is X, where X is an unknown variable. So here, before we begin further, we have two assumptions that we have to remind ourselves once again, that both the two steps are first order in both ways, okay? And secondly, now you see that this is a reversible reaction, so we expect that this reaction, after it starts, after some time, it is expected to reach the equilibrium, okay? So the reaction reaches equilibrium. That means the chemical equilibrium. All right. So this is the time t where A minus X and X is present. This is before reaching equilibrium. So we can write it that before equilibrium. Now at equilibrium, so when the reaction reaches the equilibrium, then we know that we have to talk about an equilibrium concentration. So at equilibrium, the concentration of B becomes Xe, so E stands for equilibrium, and the concentration of A becomes A minus Xe. Alright? So now we have to frame an integrated rate law. Remember, K1 and K2 is unknown, right? And the known thing is A. Okay? Means initial concentration, and also Xe can be known from different experiments. Okay? So A and Xe are known constants. And the unknown thing is X, K1 and K2. And remember, our goal is to frame an integrated rate law where we have to relate X and T, all right? And in terms of A and Xe. And of course, the K1 and K2 terms will appear, okay? So therefore, we have to proceed. So the thing is, so let's have to frame this equation first, dx dt as usual. So dx dt at any time t, it stands like k1 multiplied by the terms here, a minus x to the power 1. Okay. Now the thing is that the b is getting produced by this, but also it is getting vanished by following this term k2 multiplied by x. Okay, so we can call it our equation 1. All right. So you see, it is difficult to integrate here right here in this manner because the major problem is that we don't know k1 and k2. So we can do some much better job, by replacing by integrating the equation where finally only one rate constant would appear, either k1 or k2. So that we have to do it. But anyway, how to replace either of the rate constant from this equation? Of course, we have to use a very important condition at equilibrium. We have this equilibrium concentration. So let's remind our memory that at equilibrium, what happens? This is constant, right? So constant means at equilibrium, dx dt becomes 0. Okay, so that means the x does not change anymore with time, the concentration of B. So if that is so, then we can write this equation is equal to K1 A minus Xe minus K2 Xe. Okay? So remember, this happens exactly at the equilibrium. So if this happens so therefore what we can do, we can actually find out, okay, the K2. Okay, so our job is to find out K2 from this equation. So if I try to find K2 here, so we get K2 as K1 A minus Xe divided by Xe. Okay, so I hope you can see it. So by solving this equation here, we find an expression for K2, which is this. So now what I'm going to do, I'm going to replace K2 with this equation so that equation 1 only contains K1 and it is easier for us to integrate in a meaningful manner. Okay, so I'm going to clean the board and write it from the beginning. So we start again. We have this equation 1 originally, all right, and we have found the value for x2 is this, and now we are going to replace k2 with this one. So here dx dt becomes is equal to k1 a minus x minus, in place of k2 we have k1 a minus xe divided by xe multiplied by x. So therefore, or this is equal to, we can write it like this: at the bottom we have xe, and then at the top we have k1 a xe minus k1 minus k1 x xe minus k1 a x, and then we have plus k1 a k1 a xe x. All right, so just a minute. So here we go again. I'm sorry, the a term will not be here. Okay, so this is simply k1 xe multiplied by x. So if we look at that, okay, so we have these two terms cancelling out, so plus and minus. So therefore, we are left with this equation. Okay, so k1a, I'm going to take this common, xe minus x divided by xe, and that is basically my dx dt. All right, so now we see we have an equation there which I think we can easily integrate that. All right, so let's move on to there and let's start integrating it, and let's write the final expression. So we start again. So or we can write this equation as dx over xe minus x is equal to k1a divided by xe dt, and then we can integrate that, or if we integrate dx over xe minus x is equal to k1a divided by xe dt plus z. Z is the constant of integration, or we can write minus natural log of xe minus x is equal to k1a divided by xe t plus z. So now similarly we can put the initial conditions that at x is equal to 0, at time t is equal to 0, x is equal to 0. So the moment we put these conditions, we can figure out that this gives us z is equal to minus natural log of xe. All right. So or therefore, if we include the value of this thing over here, and if we just reorganize this equation, and then finally the integrated rate law would become t is equal to xe divided by k1a and natural log of xe divided by xe minus x. All right, so now if we take a graph plot, okay, of t versus x, then what kind of graph would you like to expect? Okay, obviously it would be kind of y is equal to mx kind of plot, and from the slope definitely we can calculate k1 because a and xe equilibrium concentrations are known. So once we know the k1, we know the entire rate equation, integrated rate law, so we can find out any value of x at any time t. The next question is how to find k2. Okay, so remember we have framed an equation relating k2 and k1 just a little while ago, so we can use that equation, put the value of k1 to find out the K2. So this is the opposing reaction in terms of dx dt. So now we are going to solve the integrated rate law, or we are going to form the integrated rate law of the opposing reaction in terms of the disappearance of the reactants, that is minus dA dt. Okay, so we are going to find out the integrated rate equation of an opposing reaction in terms of minus dA dt. So we can write the reaction like this, and of course minus dA dt becomes is equal to K1A minus K2B. So this is our equation 1. So let's take a look at what are our known constants. Known constant is the initial concentration of A, that is A naught, and of course the equilibrium concentration of A, since we are applying the same assumption that this reaction is capable of reaching equilibrium, and at equilibrium point the concentration of A is A equilibrium. Now A and B obviously are the unknown variables, and that's why we cannot integrate this equation directly. So therefore we have to convert B in terms of A, so that we have means only one unknown variable with respect to time. We can integrate that. So the question is, what is the relationship between A and B? So if we look at the opposing reaction, obviously we may find that whatever B is formed, that means whatever the change in the concentration of B, so I'm just writing here B, delta B, okay, or this. So whatever the change in the concentration of the product B, it had to come from the same but the opposite change in the reactant concentration. Okay, so this makes sense. So delta B is equal to minus delta A. It has to be, because the only way of generation of B is from A. Okay, so when B is formed, so plus delta B is equal to minus delta A. That means A has to decay. So, or what we can write, that at time t, at any time t, the concentration of B is, we can tell it as B minus, let's assume the initial concentration at time t is equal to 0 was B naught. So this is equal to minus, we can say at time t it was A, and at time t 0 it was A naught. Alright, so we have this equation. And remember, here we did not talk anything about B naught. So this B naught may be 0, may be non-zero, but at this time point we are not bothering about B naught. Okay, so let's take it some arbitrary value. So, or here we can express the concentration of B like A naught, okay, plus B naught minus A. Okay, so we get this expression for B, and therefore what I'm going to do, we have to replace the concentration of B over here. So from equation 1 we get, so from equation 1 we get minus dA dt is equal to K1A minus K2, and we have this expression A naught plus B naught minus A. Alright, or this is equal to, if we can rearrange that, because you see we have K1A here and K2A here, so if we rearrange, okay, so this becomes is equal to K1 plus K2 whole multiplied by A minus, we have K2 A naught plus B naught. Okay, so this is our minus dA dt. Okay, and we call this our equation 2. So at this point what we are going to do is we are going to apply the condition of equilibrium. So that means we are going to put that at equilibrium this minus dA dt would be equal to 0 when concentration of A reaches A equilibrium. So let's put this condition and rewrite this equation 2. So let's clean the board and work it over here. So I have rewritten equation 1 over here, and I have rearranged. That means I included the negative sign on the right hand side. So this would become the equation 3. So now let's apply the condition of equilibrium. So at equilibrium, we can say that dA dt is equal to 0 when A concentration of A becomes concentration A equilibrium. So therefore, if we apply the equilibrium condition, we get 0 is equal to K2 A naught plus B naught, okay, minus K1 plus K2 A equilibrium. Okay, so from here we try to get the value of K2 multiplied by A naught plus B naught. So or we can get the value for K2. So let's erase this part, and we can write that K2 multiplied by A naught plus B naught is equal to K1 plus K2 multiplied by A equilibrium. So therefore, we can now replace this value as K1 plus K2 multiplied by A equilibrium. So therefore, I'm going to replace directly over here is equal to K1 plus K2 multiplied by A equilibrium. Okay, so further we can simplify the above equation. So if we simplify that, it takes up the shape like this: K1 plus K2 multiplied by A minus A equilibrium. All right, so or further, you see, we can now so this part is our dAdt, of course. Okay, so that was the minus dAdt, right? So of course then we have to change the sign. Okay, so dAdt is equal to, so if the sign gets reversed, then probably we have A equilibrium minus A. All right, so let's do that. So sign gets changed, means we have A equilibrium minus A. All right, so therefore we can integrate that. Okay, so integrating, and by putting all the boundary conditions, as we have learned earlier, that if we integrate, there would be a concept of integration, and if we put the boundary conditions, that means at t is equal to 0, A is equal to A naught, etc. Then the final integrated rate equation would appear something like this: natural log of A minus A equilibrium divided by, so it's natural log of whole here A naught minus A equilibrium is equal to minus K1 plus K2 multiplied by T time. So therefore you can get the final integrated rate law for opposing reaction in terms of minus dAdt. So you may try and verify whether this would this would give to this integrated form. So still we have K1 plus K2 here. So remember, we don't individually know yet the value of K1 plus K2, but this graph can be plotted. So if we know the A versus T data, so from A versus T data, we can plot this ln, this factor versus T, and from that means it would give a straight line passing through origin. We would get the combined value of K1 plus K2, and at the same time, we have to know the K equilibrium. So the equilibrium constant would give you K1 divided by K2. So from the ratio and from this value of K1 plus K2, we can individually know K1 and K2, and at that time, we can easily get to know the concentration of A at any time t and vice versa. So that's how we deal the opposing reactions in terms of disappearance of the reactants. Okay, so next we will study the most important type of simultaneous reaction, that is the consecutive reaction, which has a profound effect in determining the mechanisms of many important applications. Okay, so we follow that next. So here we go, consecutive reaction. So the assumption is, or the basic consideration is that each individual steps are first order, number one, and number two, that is those are irreversible. That means A is only going to B and not coming back, and B is only going to C and not coming back. So therefore we will deal this reaction in terms of the as the change of the concentration of the product. That means D's CDT or something like that. Before we begin, once again, at time t is equal to 0, we have the initial concentration of A as C0, and then B as 0 and C as 0. And at time t is equal to t, it changes, so it becomes C1 and B is C2 and C becomes C3. So our goal is to, so let's write our goal over here. So what we want, that our goal is to basically to frame an integrated rate law where we can connect C3 with the time t. So that's that we want to do. And of course that equation may contain or should contain C0, because that is our known concentration, initial concentration of A we started with. And it may also contain K1 and K2. So the K1 and K2 may be known separately, so that will come to later. Or we can do the same thing with C2 also. Okay, so how C2 is related to time t with and also the equation may contain C0, K1 and K2. So before we begin, the first we have to consider also another thing, that is whatever C3 and C2 and C1 that is formed at any time t, all originated from this initial concentration C0. Okay, so at any time t, always it is true that C0 is equal to C1 plus C2 plus C3. Okay, so we call this equation 1 because this is a very important equation for us relating these things. So therefore, whenever we want to express a thing like dC3 dt or whatever C3, so C0 is known. So now we have to actually change. We have to know C1 and C2 as well. So for this we go stepwise. So that means first let's try to figure it out. What is dC2 dt? Okay. So then from this thing we will find out C3, because here whatever C3 is formed, the only way to form is C3 is equal to K2 C2. All right. So if we can form an integrated rate law for C2, we have to plug that value here and we easily know C3. So before we get to that point, how to know C2, we have to frame a differential equation involving dC2 dt. So that's what we are doing. So for dC2 dt, we can write that it is getting formed from K1 C1, all right? But again, it is dissipated into the product C, so K2 C2, all right? So we can call this as our equation 2. Okay, very good. So now let's proceed. So what else we can write? So we cannot directly integrate that part because we have the two unknown variables. So let's see if we can change C1. Okay, so C1 can be changed to C0. How? Because we know that, so it follows the first order weight law. So according to first order, C1 is equal to C naught e to the power minus K1t. Okay, so we already know that. So minus K2 C2. Or we can write dC2 dt is equal to this. Okay, so I think, so this is the constant and this is the C2. So only one unknown variable. Here we have dC2, C2. So I think we can try to integrate that at this point. So, or what we write, dC2 is equal to K1 C naught e to the power minus K1t dt minus K2 C2 dt. All right. So, or we can rearrange, or dC2 plus K2 C2 dt is equal to K1 C naught e to the power minus K1t dt. All right. So the question is how to integrate this equation. Okay. So we clean that part and we start the equation right from here. Okay. So let's do that. Okay. So let's a few steps back. And so whatever we have found out earlier is this equation dC2 dt is equal to something like this. And then, or what we do is we take this K2 C2 part over here. So dC2 dt plus K2 C2 is equal to K1 C naught e to the power minus K1t. So here the question is how to integrate. Now by looking at the nature of these two, and with that, so what we can do here is we can multiply both sides by e to the power K2t. So if we do that, so then we can write that dC2 dt e to the power K2t plus K2C2 e to the power K2t is equal to K1 C naught e to the power K2 minus K1t. All right. So the thing, why did we multiply with e to the power K2t? Because if we look at this expression, so this is nothing but, if you take a look carefully, that it is the d of C2 multiplied by e to the power K2t. All right, have you seen that? Is equal to whatever we have, K1 C naught e to the power K2 minus K1 multiplied by t. So, or, so now we can integrate that. Okay, so if we integrate this entire thing, so we get C2 e to the power K2t is equal to K1 C naught e to the power K2 minus K1 t whole divided by K2 minus K1 plus z. Z is the constant of integration. So now if we put the conditions, that is at t is equal to 0, C2 was 0, all right, then what we can get here, that this part becomes 0, or z would become is equal to minus e to the power K2 minus K1 multiplied by t divided by K2 minus K1. All right, so this is the I'm sorry, because if we put t is equal to 0, so this part becomes 1. So z becomes equal to minus K1 C naught divided by K2 minus K1. Okay. So then if we put the z value over here, and then if we just rearrange everything, then we can easily find out the expression for C2, which I'm going to clean the board and I'm going to write. Okay, so if we rearrange the last part of the equation that we got, so it gives us C2 is equal to K1 multiplied by C naught divided by K2 minus K1 multiplied by this expression e to the power minus K1t minus e to the power minus K2t, and we call that equation number 3. So look at here, this equation actually relates C2 with C naught, the constant value, and time t, and of course we have K1 and K2, alright, and these values should be known to us. So therefore we are successful to frame an integrated rate law in terms of C2. So now it's our turn to do that in terms of C3. So how we can get to C3? So remember, to go for C3, so we will follow this step. So that is, we take the help of equation 1 where C3 at any time can be represented by this C0 minus C1 plus C2. So C3 is equal to, so for C1 we can write that C0 e to the power minus K1t. This comes directly from the first order decay. Okay, and then C2 we simply plug that big value over in here, and then if we simplify this expression, so on rearranging we get that somewhat bigger looking expression, which is this C0 multiplied by 1 minus these two parts, and we call it equation number 4. Now this equation number 4, firstly, it is the integrated rate law for consecutive reaction where we can express our final product C3 in terms of time. So it's the relationship between C3 and time. We have the constant only C0 appears and the two rate constants K1 and K2. This is number 1. And further, this integrated rate law has few very important implications. Okay, so we are going to discuss quickly the implications of such thing. So you see that there are two rate constants, K1 and K2. So what are the possible relationships between K1 and K2? So we can think of 3 possible relationships. That is, number 1, where K1 is almost comparable with K2. That is a possibility. And number 2, there is also a possibility that this K1 is much greater than K2. And there is a third possibility, that is that this K1 is much less than K2. That means in one case K1 is negligibly small, and in another case K2 is negligibly small. So we will come to that part later. So now let's discuss these two parts. So where K1 is much greater than K2, so can you represent C3 in the modified manner? So that means you look at the equation 4, and if K2 is negligibly small, so if we can neglect K2 with respect to K1, so in the denominator, so it would be minus K1 over here and minus K1 over there, and then what would happen? Okay, so if you just do your maths correctly, then for when K1 is much greater than K2, or when K2 is negligibly small, you will see that kinetics would transform into C0 1 minus e to the power minus K2t. Alright? And then for the other case where K1 is negligibly small, the kinetics, that is C3, that means the integrated rate law, C3 would become C0 multiplied by 1 minus e to the power minus K1t. So what are these two means? So okay, so maybe this is appearing a little bit clumsy over here. So I may write down the two things over here. So one equation is C3, C0 1 minus e to the power minus K2t, and another part is C3 is equal to C0 1 minus e to the power K1t. Okay, so this one. So you see that we have this consecutive reaction, A going to B going to C here, K1 and K2. So when we got this condition we got this equation on condition that K1 is K2 is negligibly small. So when K2 is negligibly small, you see the entire reaction becomes a simple first order type. Okay, and you see the rate constant is only K2. So that means the entire chemical kinetics is governed by the second step, and second step obviously is the smallest step. And also here the reverse happens, that when K1 is negligibly small, the entire chemical kinetics is only governed by the first step, that is K1. So what we learn from this, that this is a multi-step reaction. So remember, in the very first lecture I told you that if it is not a free radical chain reaction, then for a multi-step reaction, the rate determining step is the smallest step, because the molecularity of the slowest step, molecularity of the slowest step becomes the order of the reaction. So here exactly we have mathematically deduced, that is, whenever we have the slowest step in a consecutive reaction, means it is so slow that we can neglect uh, that rate constant with respect to the other one, with some approximation of course. So we find that the slowest step governs the entire kinetics, and this equation over here and also this equation is simply a simple first order kinetics. Okay, so now what we are going to do at the end, that we are going to follow the graphical representations of these three cases. That means the three relationships between K1 and K2. We will find the graph plot of this entire consecutive reaction individually in case by taking the different conditions of K1 and K2. So let's. So here we discuss the case 1 of the consecutive reaction rate constants. So the condition for case 1 is the K1 is almost comparable to K2. So that means there are not much difference. So this is how it looks like. So the first reactant A, or C1, so it starts to fall following a first order rate law. So it would continue to fall like that exponentially. And after, so this is A. So after A starts to fall, obviously almost at the same time, B would start to grow exponentially. So it would grow like that. But after a certain time, means after a brief time lag, C would start also to form. But as soon as the formation of C picks up, the B starts to decay. So therefore B would reach a peak, and then also slowly B would start to decay, and C would start to gain exponentially, and it would continue to grow. So its growth may be drawn something like that. So, and so this is the decay of B, and this is the growth of C. All right, so here we see that of course in this kind of condition, the intermediate B attains maximum concentration. Okay, after that it decays and C continues to grow. Okay, so here both the steps, that means step 1 and step 2, are equally important. So next we follow the case 2, where one of the rate constant is very much higher than the other one. So here we go. We have now the condition where the first rate constant K1 is very, very greater than K2, or in other words, K2 is almost negligible with respect to K1. And I have already shown you that for whenever this condition prevails, the rate equation is basically governed by the second step, the slowest step, and this is the mathematical proof. So this is the equation. All right. So now we have to graphically represent this scenario. So the reactant A, since K1 is very high, so it would follow a very sharp decay according to the first order rate law exponentially. And then that means sharp decay of A means there would be a sharp rise of the reactant B. So the reactant B shoots up very rapidly like this. It would continue to go up. But then after a time lag, so there will be a brief time lag because K2 is very small. And then what happens that K2 would slowly build up, but once enough B is formed, it would automatically decay to C, but its decay would be very slow. So it would take a long time to get decayed, and therefore slowly the product C would start to develop, and it would follow its usual formation pathway. So this is the decay curve of B, this is the growth curve of C, and this is the decay curve of A. All right. So now the most interesting, so this will go up that, so it will go maximum up to the total concentration, that is C naught. And the most important feature of this graph plot is to show you that this graph plot actually essentially this with some approximation. So the approximation is, if you look at the graph plot, and so at the beginning there are some actions happening, but this is with respect to the 100% of the reaction, this happens within the first 5 or 10%. So if we look beyond this dotted line, okay, if we look beyond this dotted line, it would appear that the reaction is mostly B getting decayed and C getting formed. Okay, so that means this is basically the second step, because first step is so fast, so rapid, that it actually gets over well before the reaction actually starts. Okay, so therefore from an outsider it would appear as if the entire reaction is governed by this portion. So this is the prevailing part, and it would appear, right? So it would appear, if we cover this part, it would appear that this is just the second step, B to C, B decaying and C growing, and this is the characteristics reflected in the graph plot, and which the same thing can be seen over here. So in this section we understood the effect of rate determining step both in mathematically and in graphically. So in the next lecture we will follow another extreme, that is case 3, where K1 is negligibly small with respect to K2, and that gives rise to a very interesting scenario that has many applications in chemical kinetics, and that gives us to a very important and useful approximation. And we are going to learn a lot about case 3. So I will see you in the next lecture. So please continue to follow and study the lecture materials. Stay put, stay safe, and till then, goodbye.